All right, so we're going to do derivative of the first here. What's the derivative of 3 to the x? Ln 3 times 3 to the x. So that's derivative of the first times the second, plus the first exactly as we see it, so 3 to the x, times the derivative of the second. Okay, so the derivative of e to some exponent is e to that exponent back. So we will get e to the sine x back, but then we have to multiply by the derivative of that exponent, kind of like chain rule. So then we need to multiply by the derivative of sine x, which we know is cos x. Okay? And then the only extra thing that I would do here, yeah, Lauren?
Can you say that again? So the derivative of e to the
So the derivative of e to the some exponent, we get that back always.
Okay.
But then we need to multiply by the derivative of the exponent.
Is that just in this case?
That is in all cases with e as your base. Okay, so this is the derivative of the first times the second, plus the first times this whole thing is the second prime. So you always get back e to the exponent, whatever exponent it is, and then you need to multiply by the derivative of the exponent. Okay, and then what I would do here is I would just common factor. We have a 3 to the exponent x in each term, and we have a e to the sine x in each term as well, so we can take that out. And we're left with the ln of 3 plus cos x, just to simplify that a little bit. Any questions on that one? Zainab? Yep. Yep. Anytime you're taking the derivative of e to some exponent, you will get that back, and then you must multiply by the derivative of the exponent. Okay? Good? Okay. So we're going to do 2 applications today. So this one's a bit of a long setup here, but we will read it. Uranium-233 is a commonly used, sorry for the typo, radioactive material in nuclear power generators because it produces a wealth of harvestable energy as it decays. However, it does not occur naturally, so a series of nuclear reactions are required to produce it. This is called the breeding chain. Analysis of exponential decay functions is important in understanding how nuclear reactors work. The amount of radioactive material as a function of time is given by the standard function n at t. N is going to be the number of radioactive nuclei at time t. N naught, or N initial, sometimes we call it, is the initial number of radioactive nuclei. And lambda, yeah, is the disintegration constant, so how fast that particular substance decays. Okay, so we're going to look at this in terms of medical treatment. So we have a radioactive isotope of gold. It's used in the diagnosis of liver treatment. Suppose that a 6 milligram sample of gold 198 is injected into the liver, or into a liver. And that sample decays to 4.6 milligrams after 1 day. We're going to assume the amount of gold remaining after t days is given by the equation above. And the first thing that we need to do is determine that lambda variable, the disintegration constant. Okay, so we're using this formula n at t. Okay, let's just plug in what we know from our equation right now. What is our initial value of gold? Or initial amount, I should say. 6. Okay, so we're going to plug that in for n initial. So we have that 6 milligram sample. Future value after a day, we have 4.6 milligrams. Okay, so we're going to sub that in for n at t. E is just a number, so remember we don't have to plug anything in for E because it's a value in and of itself, like pi. And then we have negative lambda, which we're solving for, and time is 1 day. So we're just doing lambda times 1. Okay, so before I isolate for any exponent using log or ln, I need to make sure the base and that exponent are isolated on one side. So I just took an extra little step here, our first step here, to divide the 6 out. Zainab? You're okay? Okay. So once we have the base and the exponent isolated here, I can take either the log or the ln of both sides. Now when our base is e, we want to take the ln of both sides. But it will work if you take the log of both sides. It's just more efficient to take the ln of both sides, because then we have that ln of e that equals 1 later. So I'm going to take this guy and use power rule and bring that down in front. We know when we have any log or ln, the exponent can be brought down in front as a multiple. And then this ln of e right here, we know that that is equal to 1. So we actually just have negative lambda on one side already isolated. So I'm just going to take that negative and I'll just bring it to the other side there. Technically we're dividing by -1, but if I were to multiply both sides by -1, that also takes out that negative. So really, if negative lambda is equal to ln of 4.6 over 6, then positive lambda must be equal to the negative ln of 4.6 over 6. So that's kind of, that's our disintegration constant. We can calculate that, but it might be useful for us to leave it in this format just so that we have it as an exact value. But just for our purposes right now, we can calculate lambda, but when I plug this in for part B, I'm going to use this. But let's just calculate this just to see what it is. Yep. So we'll say, we'll just do an approximation here. Say this is equal to approximately 0.266. Okay, and what unit of measurement are we talking here? What is the disintegration constant measured in? Or what is it talking about? How fast the substance decays. So it takes 0.266 days. Or yeah, maybe, how fast? Yeah, makes sense. Okay, so when we go to calculate part B, I'm actually just going to use this expression here as my lambda, just so we don't have any rounding issues. So we're going to determine the half-life of gold through this formula. Again, if I'm trying to find how quickly something will half, I just need to make sure that I sub in something into my initial value and future value that halves that amount. So I'm going to choose 3 and 6 as my two values here. Zainab? Yeah, no problem. And then we're going to have, so if I have negative, then it's just going to be the ln of 4.6 over 6 times t. Yep.
Is it okay if we just go directly to like the ratio, like 0.5?
Yeah, for sure. Yeah, because no matter what you plug in there, you'll end up with 0.5 over here. So that's totally fine. So there's already a negative in the formula. So when I plug in the negative into an already negative part, it becomes positive. Okay, so we're going to ln both sides here. I'm going to bring down the exponent if we're okay with that. And then I'll have the ln of e over here, which we know is equal to 1. So I just need to divide out the ln of 4.6 over 6 so that I can isolate for t. Olivia.
How did you get from log 4.6 divided by 6 to like it going down? Like I don't understand.
So when I ln both sides, I'm allowed to take the exponent down in front and write it as a multiple, right? So I ln both sides. I'm just showing this being brought down all in one step. Okay? Okay, what did you get, Anil?
2.609.
And this is days. Good. So that was part B. Yep, Devin?
How do you know that it's a half-life?
It asks in the question, what is the half-life?
So how do you know that that equation is a half-life? Like,
Because I made my initial value and my future value to be halves of one another. Like, I'm calculating how long it takes for the initial sample to become half of what it was originally. So that should give me one half-life period. Okay, write the equation that gives the amount of gold remaining as a function of time in terms of its half-life. Okay, so this is essentially just asking us to rewrite the function as a half-life. We'll do it down here. So for part C, usually I have something like A at t equals A naught times a half, and then it's going to be like t over the half-life. So in our case, it uses the n at t, so we can use that rather than a at t, which is fine. So we'll replace this with n at t and n naught. Okay, we know the half-life is 2.609 approximately, so we'll just put that in for the half-life. Okay, and then if our initial sample is 6, we can plug that in and so on. I think that's all it's asking us to do.
How fast is this?
Okay, so if our initial sample is 6, we can plug it in as 6 and then just evaluate any kind of time from there. Okay, if the initial sample changes, you can change that and not, but for our scenario, we're starting with a sample of 6, so we can plug in 6 there.
How did you go from A to N?
I just changed the notation because that was the notation that was used in our initial function. So I just changed, it's just the name of a function. It doesn't really matter if I use A at t or B at t or whatever. So yeah. Okay, the last part of this is the calculus part. It asks how fast the sample is decaying after 3 days. So key here, not what has it decayed to after 3 days, it asks how fast. How fast, that's a rate of change, okay? So when we're talking how fast, we wanna think about the derivative, right? Rate of change, first derivative. And then we'll evaluate that first derivative at the value for t at 3 days. So we could use our new formula here, but I think we can refer back to maybe our original formula, the formula that we kind of used right here with n at t. And we'll do the derivative of that one. Just in case we got C wrong, right? Then we don't want to rely on that to get our next part. So I'm going to use this formula. We'll call it n at t. Our initial sample is still 6, so I'm going to leave that. And then we have the ln of 4.6, or sorry, I put 4.9. 4.6 over 6 times t. Okay, what's important for us to remember before I take the derivative of this is that the ln of a value like 4.6 over 6 is just a number. Okay, so this right here, this ln of something, is a number like any old number. Like it could be 2t. Okay, so just keep that in mind as you're finding the derivative. So when we derive this, the 6 is a constant multiple that will just kind of hang out front. Olivia?
Where did you get that? I'm confused. Will you tell me? I just got confused.
So this is the lambda that we found,
Yeah.
right? So I'm just plugging into that initial formula from the question. And we know that the initial sample is 6, so I'm also plugging that in. And that's everything that we know from the question. Okay? The derivative of e to the exponent anything is e to that exponent. So we will get this back. And then I need to multiply by the derivative of the exponent. What is the derivative of 2t, let's say? 2. So what's the derivative of the ln of 4.6 over 6t?
The ln of 4.6 over 6.
Very good, yep. Because this is just a number, right? So that's why we have to multiply by that. It is. So remember, this is just a number. The ln of 4.6 over 6 is like, you could imagine it to be the value 3. The derivative of 3t is just 3. So the derivative of ln of 4.6 over 6 is just, t is just ln of 4.6 over 6.
If it wasn't multiplied by t, would you have to use the rules, like 1 over?
If the variable was inside the ln, then you would have to use the rules. Like if it was the ln of t over 6 or something like that, then I'd be taking the derivative of a ln with that variable in it. So it'd be like 1 over t over 6 times the derivative of the inside, that kind of thing. But this is really just like a value like 2t, right? So when I do the derivative of that, I just get the constant. Okay. So I want to know why this board keeps doing this, but I also want to know what is n prime at 3. Okay, so I'm going to do the ln, 6 times the ln of 4.6 over 6, and then I will do e to the ln of 4.6 over 6, all multiplied by 3. Okay, so I want to make sure the 3 there is not inside the ln when I'm calculating, which is why I just put square brackets over it. I just moved this in here, just because it's a number. So I'm just going to do 6 times that number, and then I'll multiply it by the e to that exponent. Okay, if this really confuses you, you can calculate the value of ln of 4.6 over 6 and just use that decimal. Just leave enough decimals that it doesn't highly affect your final answer. Okay?
So you can just leave it there, right?
You can, yeah.
So I'm just gonna do that.
Sure. You do you.
Thanks.
Okay, what'd you guys get? Mark, what'd you get?
Negative 0.7.
1/8.
402,315.
402,315? 1.54?
Error, that's the correct answer right there. No, I'm just kidding. Yeah, you should get about negative 0.27 or 72 milligrams per day. Why is the answer negative?
Because it's decaying.
Oh, it's decaying. So when I say my final answer, I might say something like, therefore, the substance is decaying at a rate of 0.72 milligrams per day, rather than, I'm not going to put that negative in because I indicated that it's decaying. Okay? So we would just say, therefore, the substance is decaying at a rate of 0.72 milligrams per day. The important part of this is that the rate of change, this is the instantaneous rate of change at 3 days. So I do need to say it's decaying at a rate of 0.72 milligrams per day at 3 days. Okay? Because that rate of change is actually going to change based on what point I'm finding the instantaneous rate of change at.
We tried it next to ourselves. Or like someone do
I'd
it.
rather not.
Yeah, you can try it if you want. You guys, I'll give you a couple minutes, see if you can get started on it,
Because I think you
and then I'll start the solution, okay? I guess I should. Okay, so this is the question. See what you can do with this before we keep going. Yeah. How about that? Okay, so this is our graph. I've marked off a couple important points for you on here. You can use graphing software for this. I think that's probably important to do because we have certain areas that are like intersecting the x-axis. I've also marked off for you the maximum, and there's kind of a local min over here, and then there's another local max. I think that's about as far as we need to go. But the important thing to kind of note here is that we're going at around 1.1. We're going just past 0.5. And then what you'll notice happens is what we call dampened motion, which instead of it being a consistent motion like we're used to seeing with the sine and cosine graphs, this type of graph actually kind of takes into consideration what would probably happen naturally with this kind of shock absorber, which is like when I move a pendulum. When we think about just like a regular pendulum, eventually that thing is going to slow down, right? So it's going to be, it'll move, and then it's going to get less and less and less until it eventually comes to a stop. So that's kind of the idea here, is that we start kind of going up to a maximum, and then it will kind of, the wave will kind of get smaller and smaller as far as like the amplitude as it goes along. So that's called dampened harmonic motion. So there's our graph there. See if you can draw yourself just like a general sketch. What we need in order to do part B is we need to find a maximum, which means we need the derivative. Okay? Am I okay to scroll here? Okay. So for part B, I'm going to take our function, which is h. Come on. I don't like this, Aiden. I'm going to take our function, which is this, and we're going to start by finding the derivative, okay? So I want you to imagine this is our first, and this is our second. So we've got h prime at t equaling derivative of the first. So the derivative of the first is this guy, times the derivative of the exponent, right? So we need to multiply it by negative 0.5. Okay, that's the derivative of the exponent. Times the second, just as it is, plus the first, just as it is, times the derivative of the second, which is cos t.
Oh yeah.
Okay? I'm going to set this equal to 0, and the common factoring part of this that I've been showing you guys kind of all along is actually really important in this question. So you'll notice we have a common e to the exponent negative 0.5t. I'm going to common factor that guy out. This is really going to help me with the solving process here. I'll leave the rest in here. So we have negative 0.5 sine t plus cos t. Okay, I suppose we could take out a negative with that, but we don't absolutely need to. Okay, Now, here's the thing. I have t's in both of these expressions, which means that I can't just divide this out and try to solve, because then I'm removing one of the possible solutions, potentially. So in order for something, this is my first something, times something else to end up equaling 0, either this is equal to 0, this whole thing. So either e to the exponent negative 0.5t is equal to 0, or this could also equal 0. Right? So you guys remember, like, if I have something like x minus 1 and x plus 1 or x plus 2 equals 0, either this could be equal to 0, meaning when x is 1, I get 0 here times something, which gives me 0, or this could equal 0. That's what I'm talking about over here. Okay, so if I have a times b equals 0, either a is 0 or b is 0, or maybe both of them are 0 to make that thing equal to 0. So these are the things that I'm interested in solving over here. Okay, so here's the one thing. Any exponential function actually looks like this. It's got a little asymptote on here, and this one's actually reflected horizontally, so it's kind of like this. But it never touches 0. It's actually never equal to 0. So there's no t that can make this equal to 0 here. You guys can try as much as you want to put e to some exponent. That is going to give you 0, but it's not going to happen. Yep.
So you just know that because it's an exponential function, right?
Yeah. Also, I mean, you can try to solve, but if I take the ln of both sides and I have to ln 0, that's actually not in the domain of ln. You'll get an error in your calculator. So if you're not sure, you could try to take the ln of both sides, but I can't take the ln of 0. So this one actually has no solution. Nice and easy. We like those guys. Okay, so that guy's not going to give us any solution. I think we could probably solve this. Okay. So this one's a little bit different in our solving process than what we're used to. The big thing here is that I can't solve something when I have a sine of a variable and a cosine of a variable. So ideally, I would like to get this into one trig function so that I can solve this. So what I might do is take this guy and move him to the other side. Only reason I chose that one is because it's already negative. So when I move it to the other side, it will become positive. I'm just moving to the other side of the equation here. Okay, in order to get rid of this cos t here, I'm actually going to, this is a little bit different than what we're used to doing, but I'm actually going to divide here. And you will see the reason why I'm doing that in a second. Okay, so over here I have 1. And over here, I have tan t, yes. So that is the reason why we went that route, because I can't solve for a t if it's in 2 different trig functions. I can solve for a t if it's in 1, though. So my goal was to make this equal to tan t. Okay, now we're going to use a little bit of trig knowledge here in order to solve this. I'm going to divide out the 0.5, and when I do 1 divided by 0.5, I get 2. So 1, I'll just show you guys the step. So here, we're interested in where the tan of t is equal to 2. So if you remember the graph of tan, it kind of has those, like, it goes up in S shapes infinitely. It just keeps going. It looks like a bunch of cubics that are separated by vertical asymptotes. No, I'm on B. Are you still on A? Okay. So, cast rule. Tan is positive in 2 areas. Tan is positive in the tan quadrant and in the all quadrant. So when I do the tan inverse of 2 in radian mode, by the way, I should get my first time. And actually, I'm only really interested in that first time Because we can see from our graph from earlier that the very first time is actually going to give me the maximum, and then as my motion kind of dampens out, it just keeps getting smaller. So the very first time is actually what's going to give me our max value. Yep. Yeah, so I would have to give you the graph, I think. Or, I mean, you can always plug in values and try to graph it. But I'll give you the graph in that scenario. Yeah. Olivia?
I don't understand what the purpose of counting where it's positive.
So I'm just telling you there are two answers, but we're actually only really interested in this first answer because the first answer, like the first time that we hit that specific time is going to be the highest, and then it dampens out after that. So I'm not really interested in any of the later times. You can find both if you really want to, but I don't think we need to, is what I'm saying.
Did you ask for absolute max?
Pardon?
If it was the absolute max, it'd be that one, but if it's a local max, it could be T.
Yeah, potentially. You can check with the second derivative and see whether it's like max or min or whatever. Yep. Okay, tan inverse of 2, making sure we're in radian mode. Great. You got 1.10? Yeah? Okay, so about 1.1 seconds. I got that as well. Lovely. And we already knew that from our graph, right? So if you look at our graph here, we can actually see that the max is occurring at 1.107 seconds. So that helps us just know that we've proven this and showed it correctly algebraically. Okay? Part C just asks us to determine the maximum displacement. So we're just taking this guy and plugging him back into h at t. So I'm interested in h at 1.1. So we're just going to calculate. That should be pretty easy. Again, we want to make sure we're in radian mode so that when I evaluate the sign of 1.1, we get the correct answer. Okay, and you should get 0.514 meters. Good? Did everybody get that? Okay. We've got one more. We have until 10:15 today, so. Good? Any questions on this? Okay. We're wrapping in some information from our second unit here. We are tasked with finding local extrema. Can somebody remind me what are local extrema? What are we trying to find? Local maxes, local mins. Okay, so how do I find local maxes and local mins? Okay, so first derivative, we're interested in where the first derivative is equal to 0. So let's start with that. Find y prime. Okay, we are doing product rule here. This is our first, and this is our second. So I'm going to do derivative of the first, which is 1, times the second, plus the first, times the derivative of the second. The derivative of the second is, we get that e part to whatever exponent back, times the derivative of the exponent. Okay, and I'm interested in where this is equal to 0 because that tells me the areas of the original function that have tangents with slopes that are 0, right? Or that have maxes and mins. So again, the common factoring part of this is important because I need those two pieces in order to figure out where each of these two things is equal to 0. So either this is equal to 0, just like we did in our last question, or this is equal to 0 in order for this to be true. So is e to the 2 x ever going to give us 0? So this one actually, again, has no solution. There is an asymptote right along the line for this function at y equals 0. So it's not crossing that line. Okay? This guy, I think this will definitely give us 0 over here. I'm just going to isolate for x here, and you'll end up with negative 1 over 2. So where x is a half. Pardon? Woo. 2e? No. No. I common factored out the e, right? There's no solution to that part. Oh, you're saying you plugged it back in to get the point? Okay.
Oh, and then you get 0.139?
Yeah, you're right. Okay, we're not done yet. We're almost there. Zainab, question? Roots. Yeah, the root is 0, 0. Because when I set my original equation equal to 0, the only thing that makes this 0 is when x is 0. So it crosses at 0, 0. Okay, so I need to do a test for this. We're going to do a test in the first derivative chart. We could do that as well, if you want to do that. Okay, I guess I actually don't need this bottom part here. Okay, so the only quick thing that I need to do is just sub into my second derivative. I'm going to sub into this full second derivative over here with the e part as well. And I just want to record whether I get positive or negative in my first derivative. Sorry, that's what I meant, first derivative. Okay, so when I sub in negative 1 here, I'm just going to get a positive decimal over here, but then I'm going to get a negative in this 1 plus 2x part. So that will make this whole thing negative. And I will be going down. I will be decreasing for f at x. I have some kind of critical number here. And then when I sub in 1 here, I'm going to get, again, some decimal value times a positive. So that will actually give me an area of f at x that is increasing. So our critical number here is a local, okay, so we have a local min. The second option, guys, that was a good option, is we can find the second derivative if you want to do that. And you can test negative half in your second derivative and see whether you get a concave down area or a concave up area. If you test in the second derivative, you should have got a positive, telling you that that area is concave up and you have a local min. Okay? The last part is what Mark was saying earlier. I just want the y coordinate to this x coordinate, so I'm going to sub into our original function, which was 2 times negative half. And we will get negative 1 over 2 e to the negative 1, which gives us negative 1 over 2 e. Okay, so our local min point is negative half, negative 1 over 2e. This is the original equation. I'm just finding the y coordinate to that x coordinate. Okay, questions on this guy? Because 2 times the negative half is just negative 1. So 2's cancel, and then you're left with negative 1. Okay, so either first derivative test chart or find the second derivative and sub into that to determine whether we have local max or local min. Okay, remember the second derivative, when it's negative, it tells us concave down, and when it's positive, it tells us concave up. So if you get negative, it actually tells you you have a local max in that area. If you get positive for the second derivative, it tells you you have a local min in that area. Okay? All right. Do you guys have the numbers on your thing? Yeah. Oh, no, you don't. Okay, so it is page 289, 1 to 3, 8, and 10. Okay? 1 to 3,